This essay example, as well as thousands of others, is available in text format on our website for free and without registration. Simply Google IvyPanda Free Essays.
Experimental requirements. 2 100 milliliters beakers, 10 milliliters, and 25 milliliters Erlenmeyer flasks, and filter papers. Acetone with a molar mass of 58 g/molecular and a density of 0.79 grams per mole. Benzaldehyde with a molar mass of 106 grams per mole and a density of 1.04 grams per mole. 5 g of sodium hydroxide. Distilled water put in a wash bottle. Ethanol. Buncher funnel, filter paper, and a cork. Theoretical calculations. The limiting reagent is usually insufficient for the reaction progress. Its insufficiency leads to a stop of the reaction when the other reactant remains active for reactions. To find the limiting reagent, we first calculate the mass of dibenzalacetone produced by acetone, which is 0.025 times 234 equals 5.85 g. On the other hand, the mass of dibenzalacetone produced by benzaldehyde is 0.05 times 234 equals 11.7 g. Acetone is the limiting reagent because it produces the least dibenzalacetone. Therefore, the moles of the limiting reagent are 0.025, and the mole of the product is 0.025. This is because their ratio is 1:1. The theoretical mass of the product would, therefore, be 0.025 times 234 equals 5.85 g. Procedure. In my procedure, I mixed 0.0025 moles of acetone with 0.05 mole of benzaldehyde. I added half of a mixture prepared by dissolving 5 grams of sodium hydroxide in 50 milliliters water and 40 milliliters ethanol. At this point, I observed a yellow precipitate. This implied that a new product was forming since the original solution was colorless. 15 minutes later, I added the aldehyde ketone mixture that had remained. I rinsed the container to warrant that it was all transferred. An hour later, I swirled the mixture frequently and used a Buchner funnel to collect the products. I reapplied the vacuum and repeated this step thrice to ensure that all sodium hydroxide traces were eliminated. I dried the crystal by pressing them using cork on the filter. I then used filter papers to remove most of the water. I preserved a small sample for the determination of the melting point. I then used about 10 milliliters of ethanol to recrystallize the product for every 4 grams of dibenzalacetone. The reaction forming the yellow product was exothermic because it produced heat. The melting point was 111.5 degrees Celsius. The mass of the product was 4 grams. This mass was less than the theoretical mass, which was expected to be 5.85 grams. This was due to the lost crystals during washing and recrystallization. According to solubility chemistry, some of the crystals were dissolved at the early stages of the reaction. The product formed was an isomer of dibenzalacetone, which is E-1,5-diphenyl-3-pentadienone. Answers to the experimental questions. When 1 mole of aldehyde reacts with 1 mole of acetone in the presence of sodium hydroxide, it produces an organic substance known as benzyl acetone. This product is also referred to as benzylide neacetone. The formation of this product relies on the mechanism applied. For this reason, I will describe the mechanism involved. Since acetone has pi hydrogen bonds on either side, the hydroxyl ions produced by sodium hydroxide react with one of the pi bonds to produce an enolate. The enolate produced is nucleophilic. The aldehyde carbonyl, which is more electrophilic, reacts more with the enolate than the acetone to give an alkoxide. Water then protonates the alkoxide to produce beta-hydroxyketone, which is subjected to base-catalyzed dehydration to produce hydroxylate. The hydroxyl group in the hydroxylate was then removed to enable the formation of a double bond of benzyl acetone. We produced benzyl acetone using a base-catalyzed reaction of benzyl acetone. In this case, we use a palladium catalyst or aluminum oxide. In this process, the alkene pi bond is removed to give benzyl acetone. Equivalent proportions of the reagents ensures that the reaction takes place on only one side of the acetone producing benzyl acetone. Otherwise, the use of excess benzaldehyde would produce dibenzalacetone. In cases where excess benzaldehyde is used, traces of dibenzalacetone are expected as a result of disubstitution. If the amount of acetone used was in excess, it would also appear as an impurity. The other impurity is sodium hydroxide. In a bid to purify the product, we rinse it using water to remove sodium hydroxide. We also recrystallize it from ethanol for purity. I observed that the melting point of the crude product is lower than that of the recrystallized product. This implies that the recrystallized product was pure, while the crude one is impure. The geometric isomers of dibenzalacetone were E-1,5-diphenyl-3-pentadienone, 1E-1,5-diphenyl-1, 4-pentadiene-3-1, and 1E-4E-1,5-diphenyl-1, 4-pentadiene-3-1. A pure isomer of dibenzalacetone with a melting point that incorporates 11.5 degrees Celsius is E-1.5-diphenyl-3-pentadienone, whose melting point temperatures range from 110 to 112 degrees Celsius. I could also use the 1HNMR spectrum of dibenzalacetone in the determination of the geometric isomers produced. This could be done by comparing the pairing constant between vinyl protons. The products in the experiment have two pairs of duplets around the 5th to 7th double bonds. These double bonds correspond to two sets of protons, which are not equivalent, placed on double bonds of the compound molecule. The protons contain a similar constant, K. However, the pairing constant between cis and trans double bonds differ in a way that they cannot be assigned K as their constant. An alteration could be made to the procedure of the experiment described above to produce benzyl acetone. This could happen if I used equal moles of the reactants. If I used 0.05 moles of acetone and an equivalent amount of aldehyde, the resulting product, when the appropriate time is considered, would be benzyl acetone. In order to produce benzyl acetophenone, I could replace the acetone with acetophenone. In this case, acetophenone reacts with benzaldehyde in the presence of sodium hydroxide to produce benzyl acetophenone. The Aldol condensation reaction involves the reaction between an aldehyde and a ketone using sodium hydroxide as the alkali. Acetone is deprotonated to form a nucleophilic enolate. The enolate formed is then subjected to a nucleophile. It is protonated to produce a neutral hydroxyketone. Deprotonation takes place again to give rise to an enolate, after which the hydroxide is removed to generate an alkene pi bond. Contrary to the mechanism that was described in question 1, the reaction that gives benzyl acetone requires that the reactant's mole ratio be 1:1. It only happens when we use an equal volume of the reactants. Equal moles of reactants warrant that the reaction does not take place on both sides of the ketone to produce dibenzalacetone. The point at which the crude product melts is lower than the pure one. Impurities lower the melting point. The isomer included is trans-dibenzalacetone, since the melting point of the product obtained has a melting point between 110 to 112 degrees Celsius. This melting point falls within the range of the isomer I stated. The product contains this single isomer since the rest has a melting point that is not within this range. This report on aldol synthesis of dibenzalacetone was written and submitted by a student just like you. The IvyPanda samples database hosts thousands of works similar to this one on various subjects. Visit ivypanda.com to find what you are looking for.